work I've been doing with two colleagues. One is Karthik Balaguru, who's at Pacific Northwest National Laboratory in Seattle. The other is Samson Hagos, also at PNNL in Richland, Washington. And so the question we had was whether there's any difference in the relationship between SST and tropical cyclone intensification rates between the basins. So a simple question. And we know that sea surface temperature has a big influence on tropical cyclones. Generally, they form and they intensify where SST is warmest, which is pretty clear from this plot here, which shows mean SST and the tracks of tropical cyclones that are hurricane strength over several years, 2000 through 2008, I think it is. So clearly SST matters. And the more specific question is, if you think of just the simplest prediction model for tropical cyclone intensities, if you just said, let's take the SST ahead of the storm and regress it onto the intensification rate as the tropical cyclone passes over that location. The question is, do you have any big differences in skill between the basins for such a simple model like that? So that's kind of what I'll address in this talk. And I can answer that question pretty easily. We can just do a scatter plot. So this shows the y-axis shows the intensification rate. This is each 6-hour location for all tropical cyclones in each basin. 1998 through 2012 is the data we use. So the y-axis is intensification rate. And then the x-axis is the SST out ahead of each 6-hour location for each storm. Okay. So in the Western Pacific, we see a decent relationship. This is the percentage of the variance explained in the intensification rate by the SST. So it explains about 10% of the intensification variance. In the Eastern Pacific, it goes up to about 17% of the variance, a much stronger relationship, which is pretty obvious from the scatter. And in the Atlantic, it's only 2.5%. So the question is, why do you have these such big differences in the variance explained by SST? Very small in the Atlantic and a very good relationship in the Eastern Pacific and somewhere in between in the Western Pacific. Okay, so it's not just an academic question either. There are potentially some practical implications for this. And for example, if you look at operational intensity prediction models, statistical models that predict the intensity of tropical cyclones, in the Western Pacific, they explain about 59% of the variance. Similar in the Eastern Pacific, about 58%. And in the Atlantic, it drops down to 45%. And you remember I showed you just the simple correlation. So there's about a 13, 14% difference here between the Atlantic and the other basins. And you can see approximately this is what we see the difference between the Atlantic and the Pacific. It's about 8% to 15% difference between the Atlantic and the others. So maybe this can help explain why, at least in terms of variance explained, statistical models do not do as well in the Atlantic compared to the Pacific. And one more slide for motivation. This is a separate study, a couple of separate, more recent studies, and they show that, again, using a statistical model, if you look at the Pacific, it gives about 20 to 40% improvement over persistence. So that's the model skill. In the Atlantic, it's only 10 to 25%. And you can see this clearly here, where this is the forecast lead time going from 12 to 120 hours and the skill above persistence. In the Pacific, the blue or the purple and the red are the Pacific, much higher, and the Atlantic down here, significantly lower. So consistent with, at least in terms of these metrics, the Atlantic, in terms of statistical prediction, seems to have less skill than the Pacific. All right, so the outline for the rest of the talk, I'll go through the data and the methods that we use, and then kind of like a large-scale qualitative analysis, comparing the basins and what might be causing these differences in the variance explained, and then a more quantitative variance budget is what I'll call it, to look in more detail to quantify these differences, and then summary and conclusions. So the data we use, the 6-hour locations of maximum winds, the best track analyses for the Atlantic and the Pacific for 1998 through 2012. These are 6-hour locations. We only use tropical storm or higher intensities. 34 knots is the threshold that we use. We also decided to use a minimum SST threshold of 26, and this is mainly because we found in the Eastern Pacific there can be some real outliers in terms of really low SST as you get farther north. So to kind of have a fair comparison, we used only SSTs of 26 or higher at each location. And we redid it with lower thresholds, 25 and 24, for example, and the results were very similar. So it's not too sensitive to this, but just to be fair, we decided to implement it. And this gives us a pretty big sample size, around 2,000 in the Pacific and about 1,000 data points in the Atlantic. So we can get some pretty robust statistics from this large sample size of data points. And the atmospheric data, so of course the atmosphere can influence the relationship between SST and tropical cyclones if it correlates with either. So we want to look at that. So we use daily data from ERA interim, temperature at 200 hectopascals, which is generally thought of as the outflow temperature, winds between 200 and 850, relative vorticity, relative humidity in the mid and lower troposphere. All of these are known to impact intensification significantly, which is why we use them. The wind shear is calculated the standard way between 200 and 850 hectopascals. The steering flow average between 500 and 700, based on some previous studies, which have found that it was a good measure. So that's the atmospheric data. The ocean data is pretty simple, just satellite SST to get the pre-storm SST at each location and the cooling induced by the tropical cyclone or the cold wake. And 5-day SOTA reanalysis temperature to get the depth of the 26-degree isotherm. So the methods we use, the intensification rate, is calculated as a linear trend of the maximum wind over 6 successive 6-hour locations. So it's a 30-hour change in intensity, or linear trend in intensity. And this is it's really insensitive. The results are very insensitive to exactly how we calculate the intensification rate. This is consistent with the previous study. And the reason we do this is because if you take the average translation speed for a tropical cyclone, which is about 5 meters per second, 30 hours is about how long it takes to go 540 kilometers, which is that mean diameter of tropical storm force winds in a tropical cyclone. So at a given location, 30 hours is about how long a typical tropical cyclone will experience the conditions at that location as it goes over it. And the translation speed is the 12-hour period centered on each location, SST and cold wake. So the pre-storm SST is calculated 4 days prior to each location where the storm is. And the results aren't very sensitive to this. Either way, 2 days, 4 days, 6 days. We average it in a 1-degree box. In the Eastern Pacific, the storms in the Eastern Pacific tend to be smaller, which is why we use a 1-degree box. In the Western Pacific and Atlantic, they're larger. We use a 2-degree box. The cold wake is just the pre-storm SST, satellite SST, minus the SST 2 days after the cyclone passes. And finally, the SST, we'll call it the SST that's felt by the storm. And this is estimated at the SST 2 days after the storm's passage. And this is not exact. I mean, ideally, you would want to know the SST under the storm, but you can't calculate the satellite data. You don't have any data, and it's really hard to estimate it. So we just simply say, well, we know it's lower than the pre-storm SST, and it's probably a little bit higher than the post-storm SST, but for simplicity, we'll use SST 2 days after the storm to estimate that. All right, and then we're interested in how the SST varies along the tropical cyclone tracks. To calculate this, we calculate the standard deviation along each track and then we average all of these standard deviations from each storm. And the advantage is that this accounts for variations in track density and also in the tendency for storms to move either along or across SST gradients. So you can see this in the Atlantic. If you just took, like a grid point by grid point standard deviation, it would overestimate the SST variance felt by the storms because a lot of them translate to the west and northwest along SST gradient lines or along contours. So using this method, it gets a more accurate representation of the SST variance felt by the actual tropical cyclones. All right, so I'll get into some results. And the first is looking at this SST variance. So you can think of this as, one case, if you have no SST variability in a basin, SST is uniform, SST is going to be uncorrelated with the intensification rate, okay? And as you increase the SST variance, you have the ability to get higher predictability, higher skill using SST to predict intensification. So now this is the most basic thing that we thought of to look at. And if you look at this, you can tell immediately that the Eastern Pacific has a lot more variance along the tracks. These tend to form in the eastern region and then translate to the northwest and over the cooler SST. In Western Pacific, you have a lot less, and the Atlantic, you have less, as I mentioned before. And if you quantify, it's about 0.5 degree in the Western Pacific and Atlantic, and higher, about 0.7 in the Eastern Pacific. So this could be one way to explain why the Eastern Pacific, you have much higher predictability based on SST than in the other basins. So this seems to be consistent with that. But this is pre-storm SST, the SST ahead of each location along each storm track, okay? And we know that the cooling induced by the storm also impacts the SST that the storm feels. So we want to look at the cold wakes. And for the cold wakes, the standard deviation is slightly higher in the Eastern Pacific, but pretty similar. And the mean value of the cold wake is lower in the Atlantic, but just the mean value won't really affect the correlation. It's just kind of adjusting, the mean value higher or lower. It won't affect the relationship. So this doesn't really matter.
Right.
Yeah. Oh, yeah.
You didn't mention this. Did you remove cases that went over land?
Yes. Yes.
Just wanted to make sure.
Yeah. Yeah. So this mean value is kind of interesting, but it doesn't really mean much for this analysis. And the important question is whether you have any variability in the cold wake that is correlated with the pre-storm SST or the intensification rate. And to give you an example, let's say when you have warmer SST ahead of the storm tends to produce a larger cold wake, okay? So in this case, the pre-storm SST is high, but as the storm goes over it, it cools more, and the SST felt by the storm is going to be a lot lower than the pre-storm SST. Okay, and then if you have less of a cold wake where the pre-storm SST is lower, you'll have less cooling, and this will kind of even out the SST that the storm feels. You'll have less variance of the SST that the storm experiences, which will tend to reduce the correlation with the intensification rate. So that's the idea of how the cold wake could play into this, and I'll explain it a little bit more in the next couple of slides. So we'll look at whether the cold wake is correlated with the pre-storm SST at all. And it shows, so for each basin here, we have the cold wake magnitude on the y-axis and the pre-storm SST on the x-axis. And as you might expect, as you get to higher SSTs, you tend to have stronger cold wakes. And this is because the strongest storms tend to be over the warmest SST, so they induce more mixing and you get a larger cold wake. But in the Atlantic, as you get to the higher SSTs, so these are 1 degree bins here, 27 through 30 degrees Celsius. As you get up to 29, 30 degrees in the Atlantic, you see a big increase in the strength of the cold wake, and it's much larger than the increases in the Pacific. So this is saying in the Atlantic, for some reason, when the storms get over the very warm SSTs, they tend to induce more mixing, and you get a larger cold wake, and this is going to feed back and reduce very much the SST that the storm feels when the SST is high. And this is going to reduce the variance of SST that the tropical cyclones experience as they travel. And this effect is very strong in the Atlantic.
Greg?
Yeah?
You could explain some of this with the vertical stratification, right?
I'll get into that in a couple slides, yeah.
Okay.
Yep. Yep. Yeah, so this is only one effect. This is, yeah. Well, right, so yeah, I'll explain. Okay, so and this is pretty clear if we just look at a plot. So this is, again, this is SST cold wake at each storm location. And the blues indicate more cooling, so a stronger cold wake. And you see the strongest cold wakes are kind of in the northern and the northwestern basin. And this is exactly where the pre-storm SST is the highest. And then you get weaker cold wakes, less cooling, where the pre-storm SST is coolest in the east. So this is showing this pretty clearly. And if you look at the variability of the SST felt by the storms, so this is just the pre-storm SST minus the cold wake, you can see clearly that you have less variance in the Atlantic compared to the other basins. So this is diminishing the range of SSTs that are felt by the storms in the Atlantic. And some confirmation for this, we can look at the scatter plots of these. So the cold wake here is on the y-axis and the pre-storm SST on the x-axis. And the main thing here is in the Atlantic, you have a strong correlation between the cold wake and the pre-storm SST. So when SST gets warmer, the cold wake gets stronger, correlation of negative 0.41. And in the Pacific, it's weaker, only 0.15 and 0.19. So this is happening mainly in the Atlantic, warmer SST, stronger cold wake. And the right column is the cold wake versus intensification rate. And this is not playing a big role. It's pretty similar in all basins. If you have more intensification, you have stronger cold wakes, is all that this is saying, pretty consistently. So it's really this effect here in the Atlantic, SST affecting the cold wake. Okay, so why are the cold wakes larger over the warmer SST in the Atlantic, and why not in the other basins? That's the next question. And it turns out that the steering flow has a pretty important impact on this. And this shows mean steering flow and SST during the peak of the tropical cyclone season. Pretty uniform in the Western Pacific. Warm SST, pretty constant steering flow. In the Eastern Pacific, you have the strongest steering flow tends to be in the east over the warmest SST, which will make them go faster there and then slower a little bit to the west. In the Atlantic, it's unique because you have very weak steering flow in the Gulf of Mexico and the northwestern tropical Atlantic. And this is where you have the highest SSTs. As you get toward the east, you see stronger steering flow pushing them toward the west and much lower SSTs. So when they're over the cold SST, they go fast. When they get over to the warmer SST, they slow down. And this allows them to induce more cooling in the ocean, more mixing, and produce a larger cold wake. And this is going to dampen the variability that the tropical cyclones see or experience in the Atlantic. And we know this, just this season, we've experienced this effect. If Hurricane Harvey kind of sat off the coast of Texas for several days, very weak steering. And then there's another Hurricane Katia, I think, near Mexico, and just kind of sat there for a while. And Irma, Jose, and Maria kind of more rapidly went westward. So, again, this is just quantifying this translation speed effect. So the cold wake on the y-axis and the translation speed on the x-axis. And in the Atlantic, you see, so the cold wake and translation speed across all basins, you see a pretty consistent relationship. If storms go faster, you have less of a cold wake, which we'd expect. And the main thing here is in the Atlantic, you have a higher correlation between SST and translation speed. This is saying when the pre-storm SST is higher, you have slower translation, negative correlation. And in the Pacific, it's close to zero. So really no correlation between the pre-storm SST and the translation speed. All right, so we'll get to Gustavo's question here, I think, with the subsurface ocean. And we found that the subsurface stratification doesn't really play much of a role, at least in this in terms of this analysis. So the correlation between SST and Z26 is highest in the Atlantic. So when you have warmest SST, kind of in the Gulf of Mexico and the Caribbean, you tend to have the deepest thermocline. But if you look at the correlation between Z26 and intensification rate, it's almost zero in the Atlantic. And this is, we think, again, what's happening is it's really the translation speed that's controlling the cold wake effect and kind of interfering with any relationship between Z26 and the intensification rate, kind of on a large scale in the Atlantic. And something else that's consistent with this is if you look at the correlation between Z26 and cold wake in the Atlantic, it's lower than the other basins. So again, it's saying that just because you have a deep thermocline, it doesn't necessarily mean that you're going to get less of a cold wake, because this translation speed effect plays into it, more so in the Atlantic than in the Pacific. Okay, so summary of the ocean's role. If you look at the first thing we looked at was the along track variability of the pre-storm SST, and we found that this is highest in the Eastern Pacific and lower in the Atlantic and Western Pacific. So this is definitely playing a role in setting up these differences in the SST intensification rate correlations. And then we looked at the cold wake, and we found a positive correlation between the pre-storm SST and cold wake, mainly in the Atlantic. So the storms go slower over the warmer SST, inducing more of a cold wake, which reduces the variance of the SST that the storms feel in the Atlantic more than the other basins. So this is summarizing this. Yeah, so this is contributing. So combine the two, and really what's happening is you're reducing the variance of SST that the storms experience in the Atlantic. And as a result, you get less skill in using SST to predict intensification. So that's the ocean. That's half of it. The other half is the atmosphere. So we looked at these different atmospheric parameters that I mentioned before. And so the standard deviations are actually pretty similar. There's not too much to read into these. Wind shear, outflow temperature, humidity, and relative vorticity. But if you look at the correlation between SST and wind shear, for example, it's by far the highest in the Western Pacific. Negative 0.34, much lower in the other basins. So it's saying in the Pacific, when you have warmer SST, you tend to get weaker wind shear, lower wind shear, more so than the other basins. And this can definitely contribute to the SST intensification rate correlation, because the wind shear is acting in the same sense as the SST. You increase SST, you decrease the wind shear, and both tend to cause intensification in the Western Pacific. So we'll look at why this is the case. And if you look at the maps again, wind shear along tropical cyclone tracks, you can kind of see this. So you have lowest shear kind of in the southwestern region of the Western Pacific, and this is where SST tends to be highest. So that's explaining this negative correlation between SST and shear. So then the question is, why do you have this relationship in the Western Pacific that's not so much there in the other basins? So we looked at at each grid point, we correlated SST with wind shear. This is daily data going over the 15 years for the hurricane season. And it's clear that in the Western Pacific, you really have this large, broad area of negative correlations where warm SST translates to lower wind shear consistently. The contours are the mean SST. And then you have these bands of positive correlations in the Eastern Pacific and the Atlantic, which are unique, not in the Western Pacific. And these are due to the subtropical westerly jet in the Eastern Pacific. So this jet tends to be strongest during the time of year when the SST is highest. So you get, it turns out that this gives you a positive correlation between the shear and the SST due to this temporal variation. And in the Atlantic, it's mainly the African easterly jet that's doing it. You have the strongest or the weakest African easterly jet later in the season when the SST is warmest, so that you have this positive correlation between SST and shear. The easterly jet tends to decrease shear in the atmosphere. So it's really these large-scale patterns and the temporal variability that's dominating the SST wind shear relationships. Okay, and then other atmospheric parameters, relative vorticity turned out not to be too important. It'll act a little bit in the same sense as SST in the Atlantic, more so than the others, but then humidity is the other way. You have a higher correlation in the Pacific and lower in the Atlantic, possibly because of the Saharan air layer, which is decoupled from SST. So humidity is not going to be well correlated with SST in the Atlantic. So these kind of cancel to some extent. But we did find outflow temperature is negatively correlated in the Western Pacific with SST. And this means higher SST translates to a lower outflow temperature in the Western Pacific. And a lower outflow temperature tends to enhance tropical cyclone intensities. Yeah.
How are you defining the outflow temperature?
This is temperature at 200 hectopascals based on the ERA interim. So this is something that's acting with wind shear. So if you warm up SST in the Western Pacific, you tend to have weaker wind shear and lower outflow temperature, more so than in the other basins. So I mean, this could actually play a role also in why you have the strongest, by far the strongest tropical cyclones in general in the Western Pacific, because these terms seem to be acting together in some sense. If you have warm SST, you tend to have low wind shear and low outflow temperature in the Western Pacific. Okay, and so again, a similar plot here showing the along track outflow temperature and SST, and you can see the negative correlation. So higher SST tend to have lower outflow temperature in the Western Pacific. So again, we want to know why this is the case, and it turns out to be a pretty simple explanation. In the Western Pacific, so in all basins, the SST decreases northward. The white contours are SST. And the outflow temperature actually increases northward in the Western Pacific, the shading. And this is because of the really strong heating over the landmass of Asia in summer. So it heats it up and then it gets advected over the ocean, causing this northward increase in outflow temperature. And the other basins is the opposite. Because of the subtropical highs there, you have a northward decrease in outflow temperature in the Atlantic and the Eastern Pacific. So this monsoon land heating, turns out, is why you have this strong relationship between SST and outflow temperature in the Western Pacific. All right, so the summary of the atmosphere's role. So the atmosphere is, so the outflow temperature and the shear turn out to be correlated with SST, most highly in the Western Pacific. Negative correlations in each case, and this tends to enhance the relationship between SST and intensification rate, just because you have this covariability with the atmospheric terms. So that is kind of the qualitative summary. So now more quantitatively, we can use some statistics to see how important each of these factors is. And we'll start with the long track SST variance. This is the most basic thing that can influence the relationship between SST and intensification rate. So I showed this plot before, the strongest variance in the Eastern Pacific. So what we want to do is subsample the data so that we have the same along track SST variance in each basin. And we'll see how much that decreases the correlation between SST and intensification rate. And turns out you can do this in the Western Pacific by taking only locations with SST higher than 26.5. And in the Eastern Pacific, it's 27.1. And in the Atlantic, we'll use the Atlantic as the reference case. We won't change the Atlantic, and we'll subsample the other basins to get the same variance as we have in the Atlantic. So that's what we're doing. All right, and then this shows the results of this, eliminating these differences in the SST variance. So what I've plotted here, this is the correlation between SST and intensification rate. And so just to start, so the x-axis is the maximum cold wake. So this is a cumulative thing. So a value of 2, for example, means that I've taken all locations where the cold wake is 2 degrees or less. And when you get up to infinity, this is all cases, so taking all storm locations regardless of the cold wake. So if we look at all cases, you can clearly see that in the Atlantic, the correlation is lowest, which is that first scatter plot that I showed. Weakest relationship in the Atlantic. In the Western Pacific, it's higher. And in the Eastern Pacific, it's the highest. The dashed line here is kind of the control case before removing the variance. Okay, so that's the first thing. And the second thing to notice is in the Atlantic, you get this sharp decrease in the correlation for cold wakes around 2 degrees. And this is again because as you get larger cold wakes, it's happening over warmer SST in the Atlantic. So you tend to reduce the variance in the SST that the storms feel, and this decreases the correlation between SST and intensification rate, and this doesn't really happen as much in the other basins. So those are 2 things to notice. And then, so we took away the SST variance effect, made the SST variance the same in all basins, and that's the solid line. So in the Eastern Pacific, as you'd expect, when you reduce the SST variance down to what it is in the Atlantic, the correlations are much lower compared to the case where you don't adjust it for the SST variance, and you get a little bit of a reduction in the Western Pacific. So when you take away this SST variance influence, the Pacific basins are now pretty similar. So this means that this effect is very important in the Eastern Pacific. And of course, in the Atlantic, it doesn't change because this is the reference case. So that's the same in either case. Okay, so that's the variance. And then to remove the influence of the cold wake, we use partial correlation between the SST and intensification rate controlling for the cold wake. So we're just kind of removing statistically the influence of the cold wake on the intensification rate. That's the main term here, the red term. So this is the correlation between SST and intensification rate when we've removed the SST variance effect and the cold wake effect. So it's this partial correlation, and then we scale it by the reduction in the correlation that occurs when we remove the along track SST variance effect, because this partial correlation doesn't include this along track SST variance effect. And this is a very small term here. It's because the partial correlation is in reference to the variance that's not explained by the cold wake. So we multiply it by the square root of the variance not explained by the cold wake to retrieve the full correlation. So this will give us quantify how important the cold wake is in addition to the along track variance of SST. So again, similar plot. This is the one I showed before. So again, the importance of the SST variance effect in the Eastern Pacific. And then when we additionally remove the cold wake, we see a big jump up in the Atlantic. As we'd expect, this is where this correlation between the SST and the cold wake is strongest. So now they're starting to get closer together once we account for the cold wake effect and the SST variance effect, but there's still a big difference between the Atlantic and the Pacific basins in terms of the SST predictability in each one. So the last thing to do is to remove the effects of the atmosphere. So a very similar equation. Now we're looking at the correlation after removing the SST variance, the cold wake, and the atmospheric effects. So let's get rid of all the known factors that can affect the interbasin differences. And it's mainly this partial correlation term between SST and intensification controlling now for the atmosphere, assuming there's no effect of the atmosphere. And we have similar scaling terms here. So what does this show us? So this is the same 2 that I've showed before here for the SST variance effect and the cold wake effect. And now the bottom shows when we additionally remove the atmosphere effects. And now the main thing is, so in the Western Pacific, where we found the strong relationship between SST and wind shear and SST and outflow temperature, we see a big reduction in the Western Pacific when we take out these atmospheric effects. The other basins, the Eastern Pacific goes down a little, and the Atlantic basically stays the same. There's really no contribution of the atmosphere in the Atlantic. And So when we reduce these three effects, the SST variance, cold wake, and atmosphere, you get within the error bars, you get the same variance explained, same predictability in all three basins. So this suggests that these are the main factors affecting these interbasin differences. All right, so the summary, I made a little schematic here, and so if they're in big letters, this means it's the biggest effect in that basin compared to any other basin. So in the Western Pacific, you see the biggest impact on the SST predictability. The differences in the SST predictability is from the atmosphere, the wind shear, and the outflow temperature. In the Eastern Pacific, it's the SST variance. You have the strongest SST gradients in the Eastern Pacific, strongest variability, which is affecting it. And in the Atlantic, it's the cold wake, tending to decrease the SST variance and decrease the SST's relationship with intensification in the Atlantic. So then red enhances and blue reduces the SST intensity correlation. So in the Atlantic, really, I mean, it gets nothing. I mean, you have the atmosphere kind of reinforcing the SST in the Western Pacific, strong SST variance in the Eastern Pacific, and in the Atlantic, everything tends to reduce the variance of SST that the storms feel. There's a weak SST variance, cold wake effect, and atmosphere, all tending to suppress this predictability from SST. So we found the relationship between SST and intensification rate is weakest in the Atlantic, as I said, mainly because you have these three effects that tend to reduce it: weak along track variance of SST, weak atmospheric effects, not very well correlated with SST, and strong damping from the cold wake. As you get over warmer SST, you get a stronger cold wake, so it's damping back the SST that the storms feel. And this cold wake effect is due to the lowest translation speeds happening in the Western Basin in the Atlantic, where the SST is highest. Those are the main results that we found. So the conclusions, you could say we might be stuck with lower predictability, at least from SST, lower percentage of variance explained in the Atlantic, because these are really kind of intrinsic properties to the different basins. I don't know if you can overcome these differences, but I'll put in a little plug here for another paper, another study. And we found that if you improve the subsurface ocean stratification representation in statistical intensity forecast models, a SHIPS type model, we found that you could increase the variance explained by about 3%. So basically going from explaining 45% in the Atlantic to 48% if you do a better representation of the subsurface ocean. And that's details are in that paper that's submitted. And finally, I'll leave you with, in case you want more information, there's a paper in revision on this, and then the other paper here is submitted. And I'll take any questions. Thank you.